Okay, so in this video we're going to be talking about two LO5 problems, in particular the ones that we've done already that contain stuff about the preimage and stuff about the images of functions. Okay, so this is the preimage and the image that we are talking about in LO8 usually. Okay, so let's think about what's going on here. So we're asking whether, so we've got a function f from x to y, a subset A of the domain. We want to prove that A is a subset of the preimage of the image of A. So let's think about what that is exactly. So f of A, let's remind ourselves what this guy is. This is all the guys in the codomain that are of the form f of little a, where little a is an A. So it's the set of all guys of the form f of A, such that A is an A. You can also write this like this. So all the y's and y such that there exists an A and A, for which f of A equals y. But I think the first way is a bit clearer. All right, so maybe we can draw a picture of what's going on. So here we've got our domain x and our codomain y, and f is the function that sends each little x to f of x. Okay, so now let's think about our subset A. Maybe I'll erase this to give us a bit more room. So our subset A, and now we're wondering what f of A, or well, we're not wondering quite yet, but we're thinking about f of A, which is the subset of y that we get by sending each one of these elements in A to whatever f does to them. So we take each little guy in A, we send it over to y, we collect all those things up, that's f of A. Okay, now we're wondering what the preimage of f of A looks like, so the preimage of the image of A. And I'm claiming in the statement that that's going to contain A, so it should look like this. So let's call this f inverse of f of A. And let's write the definition of that before we go any further. So this guy is a subset of x. So it's all of those little x's in x, such that f of x gets sent to this set here, which is f of A. So the preimage of f of A is all of those x's in x, such that x gets sent to f of A when we apply f. Okay, so let's maybe boil this down even further. So what does it mean to say that something is in f of A? Maybe I can move this just slightly to give us some more room. So what does it mean to say that something is in f of A? Well, it means that it's in this set here. So it means in particular that it must be of the form f of A, or it's written a bit more explicitly here. There must exist some A such that f of A equals our guy y. So some guy y is an f of A if and only if there exists an A in A such that f of A equals y. So y is an f of A if we can write y in the form f of some little a, for a little a in big A. That's the point. So let me write this in brackets. Okay, and what does it mean for a guy x to be in this preimage? Well, it means that it's in this set So it's some x in x such that f of x is in f of a. So guy is in here if and only if f of x is in f of a. Okay, so we can use these, you can call them definitions, I guess, to answer this question. All right, maybe I can move this here. All right, so let's start answering this question. So we're trying to show that one subset is a subset of another. So we want to always consider some element of the first guy. So we consider an element A of A. And our goal is, of course, to show that it's in F inverse of F of A. That little a is in F inverse of F of A. All right, so we want to show this, and so we want to show that A has this property. So we want to check whether F of A is in, F of little a is in F of big A. So then we want to claim that this is the case because we want this to be true. So let's hope that there's a reason. So we want to say that F of little a is in F of big A because, and now let's look at the definition of what it means for something to be in big A, and that means that there must exist a little a in A such that F of A equals our guy. But of course, we're looking at F of A. So of course there exists an A in A such that, or let's say there exists a B in A such that F of B equals F of A. We just take B to be our A. Okay, so we have that F of A is in F of big A because there certainly exists an element, let's call it B of A, such that F of B equals F of A. So just to be clear, this Y here is F of A down here, and this A is our B here. Okay. So certainly F of little a is an F of big A almost by definition, because F of big A, as we've said, is the collection of all guys that you get by applying F to all the guys in A. Okay, so now we can say that this means the fact that F of A is an F of big A, that A is in this preimage just by the definition here of being in the preimage. All right, and now we can just sum up and say, therefore, we find that A is a subset of this preimage because we've shown that every element of A is an element of that preimage. Okay, so now let's look at the next question. This is very similar, just kind of the opposite. So let's consider again a function f from x to y, and now we've got a subset not of the domain but of the codomain, and we're calling that subset B. And we want to show that if we take the preimage of B and then the image, that we get something inside of B. So let's draw a picture first of all. So we've got x and we've got y and we've got our subset B here, and we look at the preimage F inverse of B, and then we look at the image. I'm claiming that if then I kind of push this guy over, I'm going to get, let me label it up here, I'm going to get something that's inside of B. Okay, so again, let's remember what it means for something to be in first this preimage. So let's say an x is in this guy if and only if, when we apply f to it, it gets sent to B. And now what does it mean for y to be in this image? It means that there must exist some guy in F inverse of B. So there must exist some guy in this set, which is F inverse of B, such that f of x equals y. So basically, we can think of it as saying y is in this image if we can write y as f of x for an x that comes from our set that we're taking the image of. Okay, so now let's write the proof using this. Okay, so as always, we want to consider an element. Let's say y in this image. Okay, so now we know that it's definitely in the image, so we can use this side of the by implication. So then we can say, then we can say, then there must exist, then there must exist an element x in F inverse of B such that f of x equals y. So now we know that x is in, or that there is some x in F inverse of B such that f of x equals y, but saying that x is in F inverse of B is kind of a weird way to say something else. So what does it actually mean for x to be in F inverse of B? We should try to simplify that and hopefully glean something a bit easier to understand. So we see here from our definition of what it means for x to be in F inverse of B that means something a bit simpler, which is just that f of x is in B. Okay? So we can just write then f of x, which we know is y, is in B. And now we're done. We've shown that y, which we initially supposed to be in f of F inverse of B, is also in B. So therefore, since we've shown that every element of this set is in B, we've shown that this guy is a subset of B. Alright, so that's it. That's the solution to these two problems. If you have any more questions, I hope this illuminated something for you and that you understand now the solutions a bit better. But if you have any more questions, please put them on the discussion board.